So we've done sum and difference, we've done product, we've done quotient, and it would seem to me like that would give us pretty much all we wanted, okay? But what if we wanted to take the derivative of something like this, right? Say h of x is x squared plus x minus 1, and you square it, right? And you'd look at me and you'd say, well, Lucas, I would square the polynomial, and then I'd take the derivative using the power rules, right? That's not too particularly hard, right? When we square that, we're going to get, looks like x to the fourth. 2x cubes are going to come out of that. 3x squareds are going to come out of that. 2x's, and then plus 1 at the end. And actually, that h of x is supposed to have plus 1. But okay, that's not too bad, right? Then if we're trying to take h prime of x, the derivative of x to the fourth is 4x cubed. The derivative of 2x cubed is 6x squared. The derivative of 3x squared, 6x's. The derivative of 2x is 2, and the derivative of 1 is 0. And that's pretty simple, right? But here's my follow-up question. What if I increase the power, right? What if I have capital H of x? It's x squared plus x plus 1. What if I raise it to the power 10? Wouldn't be too bad, right? We would just need to, it would be very, very tedious, but it wouldn't be particularly difficult. We'd have to be very careful not to make, simple, addition errors. What if I go 100? Or 1,000? Or whatever power you want there? All of a sudden, it's not quite so easy, okay? Or, what if I threw you a function like this? Say g of x is x squared plus 1, but then I stick it in a square root. All of a sudden, none of the tools we have can do this, right? When our powers here are whole numbers, we can do it. It just might be a little bit annoying, but the moment it becomes a fraction, our tools kind of run out, okay? But here's what I want you to notice, right? And this is why we actually spent some time on this last week. These are both composite functions, right? This is the capital H of x is the composition of x squared plus x plus 1 into x to the 100, right? G of x is the composition of x squared plus 1 into the square root of x. Okay? These function compositions and thinking about them is actually going to be how we calculate the derivative of these sorts of guys. Okay? And I'll draw you a little bit of a diagram. This is one that we're not going to prove. But this is what we have, right? We have some starting variable x. Maybe we apply a function f to it. We get some intermediate variable u equal to f of x. And then we apply a second function g to it, right? And we get, say, y, which is g of f of x, or it's also, notice, g of u, okay? And we can have these two derivatives talk to each other, right? If we can figure out how these two derivatives talk to each other, we can figure out how the derivative of the whole function talks to each other. And in this case, g compose f. And here's how I want you to think about it, okay? The derivative of this guy is going to be du dx, right? A change in u relative to a change in x. The derivative of this guy is going to be dy du, okay? And while function composition is distinct from multiplication, what ends up happening is that the derivative of this times the derivative of this gives us what we want, right? And here's why. Okay, again, this is not a full proof, but it is the idea. Those cancel, right? Those cancel, leaving dy dx, right? Which is the derivative we're looking for. Okay, now it might not be obvious what exactly you're being asked to calculate here, but let's actually take a little bit of a closer look. We'll state the rule in full on the next page, right? First, we'll take the simple one, right? What is du dx, right? Well, du dx is just the derivative of f. Okay, so this is f prime of x. But then what's this guy, right? What's dy du? Well, it's a small change in y relative to a small change in x. So it's g prime of u, right? It's g prime of f of x. G prime of f of x. Okay, and then when we multiply those together, that's how we find the derivative of these composite functions. Okay, stating this a little bit more formally, it's a thing called the chain rule. Okay, and here's how the chain rule looks. We're taking the derivative of g, not a very good color to color code given that I just used it, of f of x. Okay, that gives us g prime of f of x. So you take the derivative of the outside with the inside staying the same, and then you multiply by f prime of x. Okay, let's do some examples sort of to firm this up. Let's take a look at the one from the last page, right? H of x is x squared plus x plus 1 to the 100, right? This is how we'll sort of think about it, right? We'll have our intermediate function u equals x squared plus x plus 1, right? Then u prime is 2x plus 1, right? So then h prime of x is u, or rather h of x is u to the 100, right? Then h prime of x, well, first I can take the derivative and then multiply by u prime, right? Taking the derivative with respect to u is very easy, right? It's 100 u, keeping with the color coding, u to the 99, and then I need to multiply by u prime. Okay, well now I can substitute everything in, right? We have 100 x squared plus x plus 1 to the 99, because that's u, times the u prime of 2x plus 1. It's just like that, right? It's not, expanding out all of this. And if you did expand out all of this, and then take the derivative using our traditional tools, and then factor it all again, you would absolutely get this, but you don't need to, right? All we need to do is this chain rule stuff. Okay, let's take a look at that capital G of x again. Okay, capital G of x, we said was the square root of x squared plus 1, or if you prefer, x squared plus 1 to the 1/2. Okay. We'll set u equal to x squared plus 1, right? Then g of u is simply the square root of u, right? So then if I take the derivative with respect to u, right, maybe something like dg du, right, we're going to get 1 over 2 root u. U prime is just a nice little 2x, okay? But if I multiply these two together, right, and then resubstitute our u, we're going to get the derivative of g, right? So that means that g prime of x is 1 over 2 times the square root of x squared plus 1 times u prime, which is 2x. Our 2's are going to cancel, and left over we have this, right? When we're taking these derivatives, we want to separate them, right? Choose some value of u so that things separate nicely, right? Take the derivatives separately, and then multiply them back together, resubstituting in, okay? Let's do 2 more, okay? Let's say f of x is 2x squared plus 3 to the 4th times 3x minus 1 to the 5th. Now, could we expand all of these out all the way, run it as a polynomial, right, because this is just a polynomial, and calculate the derivative that way? Yeah, we could do that, and it would get us the right answer, as long as, we were careful with our multiplication. But here's a faster way to think about it, okay? Let's start with the product rule. In order to do the product rule, we're going to take the derivative of the first guy, 2x squared plus 3 to the 4th, times the second guy, and we're going to add, to keep our ordering consistent, 2x squared plus 3 times the derivative of the second, okay? And now, when we're taking the derivative of these individual ones, we can use the chain rule, right? Let's break this out into cases, right? First, we'll calculate d dx of 2x squared plus 3 to the 4th, right? We'll say we'll let u equal the natural 2x squared plus 3. Then u prime, well, u prime is going to be, looks like 4x's, because our 3 will drop. Then, if we rewrite this like this, d du of u to the 4th, that's my u, that's raised to the 4th. Those look almost identical, right? That's going to give us 4 times u cubed, right? So therefore, my derivative is 4 times u, 2x squared plus 3, cubed, times u prime, which is 4x, or 16x times 2x cubed plus 3 cubed. Okay, now let's look at the derivative of our second guy. What do they look like? We have d dx of 3x minus 1 to the 5th. Okay, u is 3x minus 1, so then u prime is just 3. right? d du, in our argument here, we're just going to have u to the fifth, right? And that's going to come out to 5 times u to the fourth. So that means to find the derivative of my original function, right, we multiply this guy times this guy, and then substitute in our value of u, right? We're going to get 5, u is 3x minus 1 to the fourth times 3. So it looks like our function, I'm going to write it at the bottom here and then move it to the next page. We're going to have 16x times 2x cubed plus 3 cubed times, should be to the fourth up there, times 3x minus 1 to the fifth plus 2x plus 3 cubed times 15 times 3x minus 1 to the fourth. Okay, let's move this onto the next page and see if we can clean it up at all. You know what, I noticed two small errors in copying this down. That should be a 4, that should be squared, and that should be squared. Okay, I find that lots of math errors happen actually when you're copying down information from up here to down here. So as a general rule, be wary of that. Okay. What we can do here is we can look for common factors amongst these two terms, and they will actually help our cleanup substantially. Okay. If you notice, for our 2x squared plus 3's, both of these terms have 3 of those. And of our 3x minus 1's, both of these terms have 4 of those. Okay? Let's copy down what's left over. We're going to have 16x's times a single 3x minus 1. Then we're going to have 15 2x squared plus 3's. Okay? So what are we left over with, right? How can we simplify this? Well, 16x and 3x gives us 48x squareds minus 16x plus 30x squareds plus 45. Okay, and then gathering like terms there, we're going to have 2x squared plus 3 cubed, 3x minus 1 to the fourth, and then that guy looks like we're going to have 78x squareds minus 16x's, and then a 45 left over, right? Is the chain rule a little bit more involved than, say, the product rule? Sure. Is it better than doing the product rule a whole bunch of times, right? Because that's something that we didn't quite touch on in the power rule. You'll have a little bit of this is covered in your homework. When you're doing the power rule, there's nothing from stopping you doing multiple power rules, right? If you wanted to take the derivative of, say, f of x, g of x, h of x, right? Here's how you could do that, right? You could treat g of x, h of x as a solitary function first, right? Then you're going to have f prime of x, g of x, h of x, plus f of x times d dx of g of x, h of x, right? And then if you do the product rule on this guy, well, then it will fall out, right? And with that in mind, this same process works for 4, it works for 5, Could you do the product rule a whole bunch of times on that? Absolutely. Is it way faster to do the chain rule? I think so. It turns out that we'll use the chain rule all the time, right? Because composite functions show up all the time. Okay, that's going to wrap it up for this week's lectures. Obviously, I haven't edited them yet, but I'm guessing they're going to come up a tad bit shorter than normal. But Tuesday's lectures were pretty long. So we'll call it there for the week, and I will see you on Tuesday.